Cool. All right. So module 2, section 11, right? So our first section of the module, second module. This module is going to focus, if you guys are, who's kind of taking a quick peek, just to kind of see what the sections are. Yeah, I always like doing that, right? So this is going to be much more focused on probability, statistics, which I think, is pretty exciting too. That like, depending on your background, you might have already had some exposure to statistics. You might kind of like feel this. Maybe if you went through schooling here in the States and everything like that, you probably had at least some exposure at like maybe high school, maybe middle school, but like some level of like statistics. My general like thing that people hear is like, usually people say like, this looks familiar. I feel like I know this, but I don't feel like I know it as well as like just to go off of it. And that's pretty familiar. And then some people who are like maybe closer in the sciences, especially, you might be like, oh yeah, like I remember doing this like not too long ago, or like, like, oh, this is something that feels actually pretty familiar to me. So just know that, everyone's gonna have a different degree, just like in the sense of degree of understanding or initial understanding, just like computer science and everything like that. So know that one thing too, I will barely claims like, hey, data science and statistics, we really should know statistics. There's a lot of data scientists who really focus on the machine learning aspect, but I'll give you a secret is that if you don't know statistics, it's hard to really understand like why the machine learning, statistical learning actually works. And also sometimes all you really need is statistical analysis versus trying to do full machine learning and everything. Okay, so I'm gonna go ahead and start sharing my screen. Oh, and who watched the video about the Kias? Or Kia, not Kias. Cool, I see some hands shake. Give me a thumbs down if you have no clue what I'm talking about. Oh no, shame on you all. It's because you guys didn't look on Slack. On Slack, there's a video about Kia. It's like a 5-minute video. Turns out they can do probability. Kia is like a type of parrot in, I think, New Zealand, if I remember that right. I saw it like a week ago, and I was like, oh, this will be kind of fun to share. Okay,
Wait,
so
I did see that because it was something about a parrot, but I didn't watch it. Yeah.
Yes, it is something about a parrot. It's just a kind of fun video, just a little informational thing. But my thing is like, if Kia can do it, so can you, right? Here, I think I can open it real quick. There you go. There's the little parrot guy. They're cute. So they can understand probability just like you can. So I'm going to go into my probability stats. Probability, no, this is all still in the repo, right? You guys all know how to find the repo from this point. Ignore this temp, that won't be there. That was messing around. Yes, so we're going to start off with not combinatorics. What am I doing? Conditional probability. So a lot of this material, I'll be honest, is straight up just from the curriculum. But if you haven't seen the curriculum yet, you'll kind of see it again. I'm just going to emphasize on the parts that like you feel like you really like should know. Not all the parts of the curriculum, I'm going to be honest, are going to be necessary for you to understand and do the statistics part. They're useful to have, for example, the laws of probability, these parts, but I'm just going to skip over a lot of this stuff. I'm going to give you the main meat that you need to focus on. Okay. So conditional probability. So one thing to know is that we usually talk about probability. I like to call probability, like people talk about sample spaces and possible events and all these things. I like to say what probability really is counting. Just turns out counting is actually really difficult sometimes. But that's really what probability is, about saying, what has happened, and what are the total number of things that could happen. And that's really what we're doing. We're counting those spaces or those different possible events. Usually you'll hear people talk about sample spaces. Note that sample spaces, the spaces part, is that you can have a continuum of events. So some things are discrete, for example, like rolling a die, right? You get either 1, 2, 3, 4, 5, 6. If you had a 6-sided die, you can obviously have different kinds of die. But you really wouldn't think of things like, like, oh, you couldn't roll a 5.5, right? That's not really a thing that we can think of. However, on a continuum, right, you can have something like, let's say, pick a number between 0 and 1 on like a number line, and you just pick something, and it could be like, oh, that right there is 0.39253455682. And it's like, oh, that's the number. Well, there's a huge continuum. So it makes more sense to think of those events as like a full space. Okay, so you hear people talk about sample spaces. Okay, making sense so far? Cool. All right. Let's get rid of this guy. Sorry, I don't usually have that guy open. Okay, so independent and dependent variables. So I'm just going to quickly show you some mathematics, and I want to walk you guys through some of it so you know the terminology, especially if you haven't like really, like I like to say, speak math. If you haven't seen this formal notation, stuff like that, it's useful to kind of walk through it. So independent and dependent variables. So independent, as you might want to kind of think, is that if we have events that are independent from each other, it means one can happen and the other one can happen regardless of what the other one is. So a simple example of this is we have two different coins, right? And if I flip a coin, lands on heads or tails, and I have a different coin and I flip it, lands on heads or tails, we assume those are independent, right? Me landing heads on with one coin isn't going to change the probability of me landing on heads or tails on the other coin, right? Does that make sense? Yeah, and I think everyone's like, yeah, that makes intuitive sense. Now, this is when like, you know, the smart aleck of the group goes like, well, you know, technically it could, you know, if you're in the same room, you could flip one, you know, the air could change the pressure and that could slightly change the probability. And those are actually 100% true. That is true. Like
the butterfly effect, huh?
Yeah, butterfly effects, chaos theory, and stuff like this. This is like the physics.
Negligible.
It's negligible in the sense that we can say, yeah, they're basically independent. Though I will say is that from a physics background, there were some research groups that kind of like purposely could try to flip a coin in the exact way. And people said like, oh, it's so hard, you know, there's so many different variables you can have. And I think it was a group in Stanford that actually designed a coin flipper that they could guarantee landing on the heads or tails every single time. And basically, they found that they could measure all these variables and stuff. But this actually, I'm going to go on tangents. I'm going to try to avoid that today. When we say something that are independent, we say they're reasonably independent from each other. And some things that we say are independent from each other are actually not really independent, but they're close enough. So like one thing, for example, like, you know, like if you flip a coin multiple times, it's possible like you are damaging the coin in some way, flip after flip, or, you know, maybe the person who's flipping it has some, you know, certain way of flipping it, and that can cause, you know, some extra bias in like how you flip the coin and stuff like this. But when we say something's independent in statistics, usually we're saying like it's reasonable to think this independent, that they're not going to be related to each other. Okay, makes sense so far? Yeah. Okay, so math notation, right? How do we describe this? So note that right here, I put independent. It should be independent if these two things are true. So if we talk about the intersection of A and B, this A and B is going to represent event A and event B. So you can think of like flip coin A, flip coin B, or you can think of it the same coin. Event A is when I flip the coin the first time. Event B is when I flip the coin the second time. Okay, and usually we denote these with capital letters, but sometimes you'll see people use lowercase. And then this P with the parentheses A, we read this as P of A, or probability of A. So this is basically saying P, and this parentheses saying this is the probability of this thing happening. Okay, so when we say the probability of, like, for example, I have intersection of A and B, what you might have sometimes, let me just kind of split this up so you can see a little better. If I see something like probability, oops, wrong symbol, probability of A and B, like this might not necessarily be the actual notation that you'll see. Like you can see here, actually, Matt Jackson, like that. There we go. Like A and B. This is saying like you're really saying, oh, it's the probability of A and B happening. Or people will even write out like, you know, probability of sunny outside. Oops. So this is typical stuff that you would like see written out and stuff like this. And the idea there is it's the probability of this thing happening. Okay, makes sense? Cool. All right. So we say, okay, what's the intersection of A and B? So what that means is basically saying, what is the probability of A and B happening? Okay, and that's what we mean by intersection in this case. And we actually denote this with an upside down U. Okay, so it's not really a U, but it's close enough to a U. So this basically is representing intersection, and that's what this little symbol right here is. I think in MathJax it's just cap, yeah. So you see cap is basically saying, oh, this intersection of A and B happening, okay? And so we say things are independent if the intersection of A and B is just the probability of A times the probability of B. So mathematically noted like this, we just say probability of A intersection B, or probability of A and B happening together, equals the probability of A times the probability of B. Okay, all making sense? Cool. And note that this probability will always be between 0 and 1. And you can think of that like a percent chance. I think these are things that people relatively know, but ask questions if you're not sure, right? So basically, this is happening because this intersection right here is saying, okay, these events can both happen. And if they're independent, you don't care about basically if A and B affect each other. Basically, it's just the probability of A happening and then times the probability of B happening. Okay, sound good? All right, so now we have here is the union of A and B, right? So A and then this kind of U, like looking like a U thing in B. And you can see it's represented in Math Jackson's cup, just so you know how to write these things down. I think the curriculum also has something similar. And what this is basically saying, if we combine all the events of A and all the events of B together like this, they're independent if the probability of A, or this is equal to the union of A and B, is equal to the probability of A plus the probability of B, and then minus the intersection of A and B. And so what this is really trying to say is that we're not double counting, essentially. So this, for example, the diagram from the curriculum shows basically the probability of A union B. So you can see here, like you can imagine this is A, this kind of blobby thing here, and this over here, this is blobby thing, which you can see is in red and in blue. Okay, so we're saying that, okay, the union of this together, when we combine all of the possible things that happen together, okay, is just going to be probability of A plus the probability of B. So note that we have a little bit of extra double counting here because they're intersecting, and then minus this probability A union B, or sorry, intersection B. It's just going to equal this guy. And that's like, yeah, that makes sense. We can see like those shapes like make sense. And this is what we talk about probability space. So this is kind of like an arbitrary, just like representation of these things. Note that basically these can be on a spectrum and stuff like this. And that's why we represent them as spaces. Okay. Sound pretty good? Now I will tell you right now, do you need to know this? Like off the top, like, oh, it's independent because of this thing? No. Like in all likelihood, you probably understand what independent is just by knowing the situation. But we can actually mathematically define this. And so we can actually say something is like we can define independence as a mathematical item. And you'll notice this very commonly in a lot of the mathematical language. We take something that we intuitively understand, or maybe we start with an intuition and we kind of move forward and say, what does that imply? And then we say, well, what's the mathematical formalism? So we can kind of like write these things down and do the mathematics with it. Okay, cool. Any questions? I know I kind of walked through this a whole bunch, but I think seeing notation, seeing pictures and stuff is a really good part. Okay, cool. So the next part of this is something called disjoint. So in this case, we say something's disjoint if A union B is equal to just PA plus PB, right? So now that's a little different from here. And so if you imagine if something is disjoint, when you think of disjoint, you can probably think, what does that mean? Sometimes mathematicians say the really great words and like the right things that make sense. Disjoint means disconnected, right? Not connected in this thing. Sometimes they don't do the best job naming things, at least for the common folk of like non-mathematicians. But that's exactly what it means. It means that like if we were to have two different shapes, for example, just kind of quickly drawing here. Oops, can I draw? Yeah. These would be disjoint, right? So these two probability spaces are disjoint from each other. They're not touching, basically. There's no overlap, right? And that makes sense, is that if you still have PAUB, or sorry, PA, probability of A union B, you don't have this part because there's no, this extra part. This is always 0. So note that disjoint and independent, right? Those are you can have both of those things, okay? You also don't need to have both of those things technically. So just note that difference and such, and note that subtlety. And I think there's a little picture here I can kind of show you very quickly. That's very similar to this one from the curriculum, and you can see here, yeah, ooh, really, real mind-blowing stuff, right? So again, like I said, like probability in my mind is just counting and kind of like seeing these parts. It's just that sometimes the counting can get really difficult. So, okay, so we got independent and disjoint. Sound good? Cool. All right. Note that if things aren't independent or aren't disjoint, it doesn't mean we can't do any math with it. It's just we have to be more careful with basically this crossover, basically saying how things can affect each other. And that just adds some more complexity to it. But this is usually what we want is independent and disjoint. All right. So I'm going to show you some probability theorems that the curriculum kind of goes through. They label as product rule, chain rule. First of all, don't feel like you have to like memorize these things or you have to like write these down, or, you know, back in the day, I remember people talk like flashcards and stuff like this. If it helps you just because like you want to kind of do this, awesome. But I think in general, you kind of get the feel for this. So the product rule, and this is always true right here, is that the probability of A intersection of B is just equal to the probability of B times the probability of A, and I'm going to read this off to you, this funky guy right here, is it's the probability of A such that the event B happens. So usually we'll say like probability of A given B, or probability A such that B, okay? And what this means is like, what is the probability of A happening such that B happened too? Does that make sense? So that's why also like given that B happened, and that's usually the kind of the mathematical, like the way you read this. So, and note that this is also equal to the probability if the union, sorry, intersection, yeah, messed myself up. The intersection is also equal to the probability of A times the probability of B such that A happened. So again, this is basically showing you, it's like, okay, that's how we know the intersection between these two. And this is because you can have overlap and stuff like this. Note that if you're independent, this should still hold. This is always true, no matter what, if it's independent or not. But if it's independent, we'll see the probability of A intersection of B, as we saw before, is just the probability of A times probability of B. So why is this true? Why did we go from this thing right here, or come from this thing up here to this? Can someone try to give an example or try to explain away, like, if this is always true, how do we get from here to here if it's independent?
I don't know, but if they're independent, then one shouldn't affect the other, right? So it shouldn't be, you know, you couldn't say the probability of B given A if A has no effect on B.
That's right. Yeah, that's right. And basically, you said it just right, Vero, is that the probability of B happening given A, well, if they're independent, B doesn't care what happens with A. It's always the same. Probability of B happening given A happens. Well, B doesn't care what happens with A. So that's just going to equal the probability of B. That makes sense? So if A and B are coin flips, for example, and we know two coin flips are independent from each other, B doesn't care, the coin flip B doesn't really care what happened with the first coin flip, right? It's just always going to be whatever the probability of B is. And that's why we can simplify this guy right here to something like this. And note that it doesn't really matter if you treat A or B, you know, like you could swap things and it would work out the same. Okay, and that's important. I think this is kind of nice to know. It's like, okay, this is a good gut check. Like, yes, this makes sense. Like, we would expect these things. Okay, sound pretty good? All right, cool. All right, so next rule, which chain rule, I'm not even gonna spend too much time on it because always too many numbers and everything. So this is from the curriculum too, but I think kind of helps kind of just going through. So this bottom one right here is just gonna be the more general rule. But the product, you can extend the product rule, which remember is just this guy right here, right? Is that A intersection B is equal to the probability of B times probability of A given B, okay? So what we can do is like, well, okay, with let's say 3 variables, we have A intersection B intersection C. We can use the commutative property. Turns out that works. It's kind of a hand wavy thing if you didn't think of. Not commutative, sorry, associative property. So we basically say, okay, B and C are associated together. So the intersection of B and C together, and then A intersected with whatever B and C intersected together. Okay, that's what we're really doing. And so we break this down, it's like, well, okay, what's the probability of B and C together? Well, that's just this guy right here, right? And then intersected with A. Well, we know how to do this because we've seen through the product rule. We just take like, okay, let's just say the probability of B, right, is really this guy right here. So we can say, okay, that would just be probability of B intersection C, which is what we see right here. And the second part is probability of A given B. So this would be probability of A given B and C. And you can see that's what this is right here. Okay. So note that we're just kind of breaking this down a little bit. And if you kind of swap, basically, the way I like to do this is if I were to replace this with X and Y. So if I were to kind of replace this with X and Y and then say, okay, which one's X, which one's Y, and then replace it in there. And note that this second one right here, I think I also copied from the curriculum, it's just breaking down even further. It's like, well, okay, if we can break down this guy to here, it's like, well, we can break down this probability of B in C, break it down even further, right? Which you can see here, probability of C times probability of B given C. So that's kind of how you can do the what's called the chain rule. So basically we're kind of using that product rule over and over and over by going deeper and deeper and deeper. And you can see here, curriculum kind of shows a little quickly, if we had A1 all the way through AN, right? You would just have essentially A given all these other ones times probability of A2 given all the other ones, right? So then it gets smaller and smaller and smaller until we get basically to the N part. And note that this is the mathematical notation, right? It depends how familiar you are. It's N minus 1 given AN times the probability of AN. Okay. So this is basically just a way to mathematicians can write this. And if you were really fancy, you'd probably write this in a summation versus like, or not, I guess technically like, not summation, prodication? I never said a word like this. Anyway, you could write this even more condensedly if you really wanted to. But does this make sense to people? How we got from, at least from here, down over here, we just said, oh, they're associating it. We break it down, we break down even more. And then if we were just to do this with a whole bunch of them, that's what we would get right here. Okay. Cool. Basically, the real big thing about this is to realize in the chain rule is that you don't have to consider the other events that were such that. So note that this, instead of having like A3 and all the way through N, and then at the end here, A3 all the way through N, we just get smaller and smaller and smaller and smaller, considering less and less things. Okay. Cool. All right. So skipping over that to Bayes' rule. So Bayes' rule, Bayes' theorem, it's said either way. We'll talk about this more, but I just wanted to, it's such an important aspect, and you'll hear people talk about Bayes all the time. Like literally people say Bayes is a badass. Like I will tell you a secret, Thomas Bayes, who is the person who came up with Bayes' theorem, never actually wrote down Bayes' theorem. He thought it was literally so trivial and so obvious that like, why would you have to write this down? This is just kind of given. So we'll talk about this in naive Bayes classification, which is going to be one of our first, I don't know if it's necessarily our first, but it's one of the early on of supervised machine learning algorithms, which actually does a really great job in doing things like spam detection. But basically all it is this guy right here, is that we saw from here, it's just the probability of A given, probability of A intersecting B equals probability of B times probability of A such that B. Well, if we rearrange this now, so if you imagine we just divide out probability of B, we get probability of A given B equals PA and B divided by probability of B. So this is how we're able to get this like formula. And this is usually, if you look at Bayes' rule or Bayes' theorem, you'll see this guy right here. So I just wanted to point that out because we'll see him again. Just notice just a reorganizing the product rule, which again, Bayes is like, okay, that's pretty cool. But once we go one step further and say, hey, well, we can use the product rule again and split this up, right? And you can see here, it says this is the part that we'll see is the probability of B such that A times PA divided by PB. So this is like, I think was one of those things like, oh, this is just like reordering the parts until like it works fine. Like, okay, that's cool. The reason why this is super powerful is that we can say the probability of A given B that happens based on if we know the probability of A and the probability of B, but also we can just say the opposite. It's like, what's the probability of B happening such that A happens? And that's kind of one of those things that's really powerful. It's like, now we can look at probably like the events from probability B and actually get a pretty good job on this. And usually what's really cool is that we usually know most of these from just empirical evidence by basically measuring things. And we can actually determine now the likelihood or, the probability of some event happening based on other events. So again, we'll talk about this more in the future, but it's such an iconic theorem in probability that it's worth like mentioning. Okay. Sound pretty good? How are we feeling about math notation? It's a lot of, a lot of symbols and everything like that, but hopefully you're getting a little exposed to it. And I think it's helpful to hear people talk about it versus like just staring at it for a while. And like, if you've never seen it before, or like it's been really a long time since you've seen it, it's useful to kind of know this happens, or like how to read this and how to look at it. Okay.